Welcome to IUPAC Digital Network. Organic chemistry is defined by its molecular architecture, and carbon provides the structural foundation for the entire system. This rapidly forming lattice demonstrates the raw building capacity that creates everything from pharmaceuticals to industrial polymers. These interconnected spheres highlight the specific traits that make carbon so versatile. Through tetravalency, a single carbon atom forms 4 covalent bonds. When combined with catenation, the ability to bond to itself, carbon constructs complex chains, branches, and rings of virtually any length. Carbon achieves these shapes through orbital hybridization. Mixing one s and 3 p orbitals creates a tetrahedral sp3 carbon. Using 2 p orbitals yields a trigonal planar sp2 geometry, while 1 p orbital creates the linear sp bonds of ethene. We organize these structures into homologous series, families of compounds sharing a general formula and a specific functional group. These groups serve as the reactive centers, determining exactly how a molecule responds to its environment. This organic reaction map displays those connections, linking alkanes, alkenes, halogenoalkanes, and aromatics. Every line represents a reliable pathway to convert one functional group into another. Organic chemistry operates as a logical system where electron flow governs every interaction. By recognizing the regions of high and low density on this map, you can predict the outcome of any chemical reaction. Our deduction begins with the alkanes. These are saturated frameworks containing only single sigma bonds. Because these bonds hold their electrons tightly between the atoms, alkanes remain highly stable under normal conditions. Even in stable frameworks, the arrangement of atoms dictates properties. This side-by-side comparison shows structural isomerism in butane and but1ene, where the skeleton or bond position changes. In contrast, but2ene demonstrates geometrical isomerism, where restricted rotation around the double bond creates distinct spatial arrangements. Forcing a stable alkane to react requires significant energy. In the free radical substitution of methane, ultraviolet light fractures a chlorine molecule into 2 reactive radicals. This animation uses half-headed arrows to track the subsequent electron flow through propagation and termination. Alkenes and alkynes introduce unsaturation via double and triple bonds. These multiple bonds contain pi bonds, which position electron density above and below the carbon axis. This creates an exposed, electron-rich target for chemical attack. In this electrophilic addition, propene's double bond attacks the hydrogen in hydrogen bromide, leaving a carbocation intermediate. By Markovnikov's rule, hydrogen joins the carbon with more hydrogens, forming a stable secondary carbocation. The bromide ion then attacks to produce 2-bromopropane. In physical lab tests, an alkane leaves bromine water orange, but in alkenes, pi bonds trigger immediate addition, rapidly decolorizing the solution. This same addition mechanism is used to link thousands of alkene monomers together. Under high pressure, the pi bonds of ethene molecules continuously break and reattach, constructing the massive, saturated chains of polyethene. While converting reactive alkenes into stable alkanes creates durable materials, it also produces a significant environmental challenge. Because these saturated polymer chains resist degradation, discarded plastics, like those in this urban waste pile, persist in the environment for centuries. We move to the alkyl halides, where carbon bonds to a halogen like chlorine or bromine. We classify these as primary, secondary, or tertiary, based on attached carbons. Because halogens are highly electronegative, they create a polar CX bond. The halogen pulls electron density away, leaving the carbon with a partial positive charge that attracts incoming nucleophiles. These halides resolve attacks differently. SN2 is a single-step, simultaneous backside attack. Conversely, SN1 sees the leaving group depart first, forming a carbocation. Surrounding methyl groups donate electron density to stabilize this positive charge, allowing the 2-step process to proceed. Strong bases introduce a competition between substitution and elimination. The final product depends entirely on the temperature and the choice of solvent. Heating the halide in aqueous sodium hydroxide encourages the hydroxide to act as a nucleophile. It substitutes for the halogen, yielding an alcohol. However, using hot, concentrated ethanolic alkali forces the hydroxide to act as a base. It removes a hydrogen from an adjacent carbon, eliminating the halogen to form an alkene. These reactions gave rise to industrial chlorofluorocarbons, or CFCs. For much of the 20th century, these halogenoalkanes served as the primary refrigerants and solvents found in vintage appliances like this one. While industrially useful, the stability of CFCs allowed them to reach the stratosphere, where they caused the depletion of the ozone layer. Modern chemists use these same reaction pathways to design safer alternatives that degrade before reaching the upper atmosphere. Benzene lacks isolated double bonds. Overlapping p orbitals create continuous rings of delocalized electron density above and below the plane. Proven by its geometry, every carbon-carbon bond is identical in length. This immense delocalization energy makes benzene highly stable and resistant to addition reactions. Benzene instead utilizes electrophilic substitution to preserve its ring. In this nitration mechanism, a nitronium electrophile is generated and attacked by the ring's pi electrons. This forms a temporary sigma complex before a hydrogen proton is lost, restoring the ring's aromaticity. When we add a methyl group to form methylbenzene, the reactivity increases. Alkyl groups donate electron density, pushing additional charge into the aromatic system. This increased density makes methylbenzene more reactive than benzene, and it directs incoming groups primarily to the 2 and 4 positions on the ring. Specific conditions dictate where the reaction occurs. Reacting methylbenzene with chlorine and an iron catalyst targets the ring, whereas using ultraviolet light without a catalyst targets the methyl side chain through free radical substitution. The side chain remains a point of chemical vulnerability. Treating methylbenzene with hot alkaline potassium manganate oxidizes the entire methyl group into a carboxyl group, producing benzoic acid. Handling these aromatic compounds requires strict laboratory safety. As shown here, researchers must use fume hoods and protective equipment because benzene and its derivatives are often toxic and carcinogenic. While aromatic delocalization provides the structural stability needed for pharmaceuticals and dyes, harnessing that power safely requires precise synthetic control and rigorous safety measures. Our synthesis map is now fully populated. Hybridization, pi bonds, and polar bonds connect these different families, allowing us to predict the behavior of complex molecules. We trace these pathways to engineer specific compounds. Converting ethene into propanonitrile requires an initial electrophilic addition with hydrogen bromide, followed by a nucleophilic substitution with ethanolic cyanide to extend the carbon chain. Test your own understanding with this final synthesis challenge. Using the pathways we've explored, identify the reagents and conditions needed to convert ethane into ethanol. Mastering organic chemistry means mastering the predictable flow of electrons. This understanding empowers us to design the molecular structures shaping our world. Thanks for watching. For more course modules and to verify your synthesis route, visit www.iupac.cc.